Okay, so I'm doing problem number 3 from test 1. And it says a soccer ball of mass 0.3 kilograms is rolling with velocity 0.02 meters per second. Your kick delivers an impulse of 3.40 newtons per second. The ball starts from an initial position of 0.46 meters and rolls with a net force from the air in the grass with a magnitude of 0.4 newtons and pointing in a direction opposite to momentum. So part A of the question is asking for what is the total momentum. Well, momentum is equal to mass times velocity, and we have both of those. And so the mass times velocity is the 0.3 kilograms times the 0.02 meters per second. But it also includes the impulse in the question, and we know that impulse is equal to F net times delta t, which is equal to delta p, which is equal to change in momentum. So we want to add the impulse, which is 3.40 newtons per second, to the mass times velocity to get the total momentum. And once we do that, we can calculate and get 0.6 kilograms per meters per second. So that will be the first part. And then using that information, we can help us solve the second part of the problem, which is asking for the position and the velocity after a time step of 0.5 seconds. Well, to do this, we have some information already, including the initial position, and we also have the initial velocity, and we have the magnitude of the force, which is 0.4 newtons. But we need to find a final momentum, because in order to find the final velocity and the final position, we need to find a momentum. So in order to find a final momentum, the equation would be, we'll need the net force. So for net force, they give us 0.4 newtons, but that's the magnitude. And we have to find the vector, because we need a vector. So we can find that the F net vector is equal to magnitude times the unit vector of the momentum. And to find the unit vector, we just do the momentum, which is 3.4, 0.6, and we divide by the sums of all the square roots of the sums of the squares. And we get 0.985, and 0.174 for the unit vector of the momentum. And we just will multiply that by the magnitude. And since it says in the opposite direction of the momentum, that's why we use the negative sign. And after we do all that, we get negative 0.394 and negative 0.0696. And that's the F net. So using the F net, we can find that the final momentum is equal to the initial momentum plus F net delta t. And we have the initial momentum, which is 3.4, 0.6. And then we can use the F net we just found and times the delta t, which is 0.5, because that was the time step. And we get 3.2 and 0.565 kilograms per meters per second as our answer for the final momentum. But the question is asking for final velocity and final position. And we can find the final velocity by approximating the final momentum divided by the mass. And once we do that, we get 10.7 and 1.88 meters per second as the final velocity. And using the final velocity, we can find a final position. The equation for the final position is the final position is equal to the initial position plus the final velocity times delta t. And we're given the initial position in the problem, which is 0, -4, and 6. And then using the final velocity we just found, which is 10.7 and 1.88, we can multiply that by delta t, which is 0.5, and we get the answer of 1.346.94 as the final position. Okay, and then the third part of the problem is asking for the final position and velocity after 1 second, which will be an increase of half a second from the first time step. So again, we just do the same process, but using slightly different numbers. So for the final momentum, it's the same equation with the initial momentum plus F net delta t. but we're using the initial momentum from the final momentum of the first time step, which is 0, 3.2, 0.565. So we do that, and the F net is still the same since nothing's changed, and the delta T is 0.5 again, even though it's after 1 second, but it's a difference of half a second. And after those calculations, we get 0, 3.01, 0.53 kilograms times meters per second. And then, again, asking for final velocity, so we can approximate that the final velocity is equal to the final momentum divided by the mass. And after that, we get 0, 10, and 1.77 meters per second for the final velocity. And again, using the final velocity, we can use it to help us calculate the final position. And the final position is equal to the initial position plus final velocity delta t. And we're using the initial position, which is the final position from the time step before, just like with the momentum. So the initial position would be 0, 1.34, 6.94, and then the final velocity, which we just calculated, and delta t. And the final answer will be 0, 6.35, and 7.83 meters. And that'll be the final answer to our problem. Thank you.